looking out for you here. What? I have. It ruins it. So, with the optic stuff out of the way, or at least the what we call the geometric optic stuff out of the way, we're getting into, for a few days here, we're getting into what we call physical optics, which includes things like what we call interference. Okay, so I don't know, back like a month or two ago, we experienced interference in the form of like water waves. You guys remember that? Remember?
Yeah, you did. There's like points of interference.
Yeah.
You nodal line.
You remember this?
No, that's a nodal line.
So we had those ripple tanks in the dark room, and you basically had two sources of waves, those little spheres that would bob up and down, and then you were able to see, hopefully see, the interference from those. Yeah. So as those waves come out, they would interact with each other. You'd have these stripes where basically those waves cancel out. There, right there. Right there, right there. Do you guys remember what those were called? Those locations where we have canceling out?
Antinodal or nodal?
Nodal line.
Those are nodal. Okay. What kind of interference was that? What? Direct?
Yeah.
Not quite. It does start with a D.
Distal.
Not distal. What are they doing? What are these waves doing to each other? They're canceling out. They are destroying each other. So it's destructive interference. Okay.
Is it constructive interference?
Right here, right down the middle, where these waves add together, you get constructive interference. Okay? So now it turns out that anything that has wave properties, or anything that is a wave, you can get constructive and destructive interference. Okay? The last month or so we've been looking at, or the last few weeks we've been looking at light. Okay? Light is a wave. Therefore, light can do this constructive and destructive interference thing. And that's exactly what we're going to be looking at today, is what happens when light constructively and destructively interferes. We're going to do that in two different ways. Okay? The first way that we're going to look at is we're going to take what we call double slit interference. That's where we do almost the same thing as what you saw with those water waves. We're going to have basically two very, very narrow sources of light, and we're going to see that when that light comes through those very narrow sources, those very narrow slits, on a screen way over there somewhere, we're going to get this constructive and destructive interference pattern. Okay? We're going to see regions of light and dark and light and dark and light and dark. Where we see light, we've got constructive interference. Where we see a dark spot, we've got destructive interference. Light waves will cancel themselves out. Right? Once we do that, we'll derive a couple of relationships there. We'll also do later on a single slit. It turns out that light can do this through one single narrow slit as well. So we'll see that relationship, how that works out also. The ultimate goal here is for tomorrow, for us to be able to go in the darkroom and actually see this stuff and measure it for real. We're going to take, first of all, a laser of known wavelength, and from that, we're going to be able to determine two things. One, the separation of a thing called a diffraction grating, and then two, we're going to figure out how wide one of your hairs on your head is. We're going to use diffraction to figure out the width of a hair. Okay, so bring your hair tomorrow. Once we figure out the width of your hair, we can then take a laser of a different wavelength, an unknown wavelength, this one, right here. Okay? We don't know the wavelength of this thing, it's written on here, but you don't know it. But using the known width of a hair, we can figure out the wavelength of green light, or green laser light in that case.
So are we using multiple colors to like cancel, or is it just...
Nope, it's got to be monochromatic.
Is that one of those things that like burn a hole in the space?
No, not this one. It's only 5 milliwatts. All right.
If you held it long enough.
So that's a great question that David asked actually. This works best when we have what we call monochromatic light. Mono meaning one, chromatic meaning color. One color, a single color, which is why lasers are so good for doing this stuff with.
So what if you use two white lights?
Use two white lights, then you might get, if you do it just right, you can get interference that you'll get colors, you'll get rainbows. And we'll see some examples of that as well. Yeah. This is just copper sulfate, something like that. Hey. All right, so let's get to it here. Here's what we're looking at. Okay. I'm talking about, all right, when I'm talking about this interference stuff, these interference patterns of light and dark bands, this is what I'm referring to. So you take a light source. In our case, it's going to be using lasers. And you take that light source, you can imagine that those waves going out, from some location, and they're going to hit this barrier. They're going to hit this barrier that has two slits in it. Okay? So now you're going to get individual waves of light coming out of each one of those slits, kind of like you have those two bobbers in the water tanks. Okay? The effect of that is that at some point on the screen way over here, you're going to get those waves to add together to give you a constructive interference. You get a light spot. But off center a little bit on either side, you're going to get those waves to destructively interfere. They're going to be off by exactly half a wavelength. So they're going to destructively interfere. They're going to cancel out. So you get a dark spot. You get no light there. Okay? And again, a little farther out, you get another spot where you have constructive interference. And farther out yet, you get another spot, another two spots, and then you have destructive interference. These just keep on going. Light, dark, light, dark, light, dark, etc. Okay? So you have these different spots where you have adding or subtracting. Right? That's what we call two-slit interference. And this is the interference pattern that we end up with. Hi.
Hello there. Sorry about that.
That's all right. So, let's see if this actually works. Thank you.
Thank you.
We'll see if this actually works out.
What?
So I'm going to be shooting this at some of y'all's heads.
Okay.
So watch out. Look at the size. I mean, look at the size of this laser. Imagine what it's going to do to your face.
No, it's right.
Could that blind you, man?
It's a gun.
This thing is not that big
Does it
because
shoot like a laser gun? So like
it's not this big because it needs to be. Well, it is.
It's just to get it.
Exactly.
Whoa.
Guys, the reason that it's so darn big is because it was built in 1994. All right.
Oh, it's 94.
1994.
Cooler than me there.
So you can kind of see that spot there. Yeah, from a laser that size, you get that? Really? Yeah, 1994. These days, in, 2014, so we're now 20 years after that, you can get a laser way more powerful than that in like the size of a pen. Okay, so to give you an idea of what 1994 lasers look like compared to today, that's only a 20-year difference. It's got a huge difference in technology. All right. It's just fun to have this in the classroom because it's huge and it's ridiculous. And we like things like that.
People freak out about it.
Yeah. Okay. Now what I've got is this thing. You kind of see it against the window. It's got some looks like holes or whatever in it. It's got several different kind of configurations of things. It's got single slits, double slits that are very close together. It's got things called diffraction gratings, which we'll talk about eventually. But what I'm going to do is I'm going to run this laser light through one of these double slits. Okay, and we're going to see on the screen what we get. There you go. Okay, so you can very, very obviously see that we have those light and dark bands, right? We've got the central, the brightest of the light bands is called the central maximum, and then if you go to the right of that central maximum to the next maximum, we call that the second maximum, or we call it the n=1 maximum. You'll see what I mean by n in just a second. So very easily we can clearly see that we do get these interference patterns from monochromatic light through a double slit. All right, so let's try to figure out mathematically what's going on there. I need a clapper. Do anybody have a clapper? Oh, it didn't work.
Oh, I was clapping.
Light clapper, so I can turn the light on without having to go away.
Oh, I was trying to turn it off.
Well, I appreciate the enthusiasm.
Then just everybody screws the clapper. It's like
But I have a way of turning it on. The clapper that I have control, it only responds to my.
Really?
Yeah.
or your voice.
No, I'm saying I need one.
Oh.
Not that I have one, I need one. He was a wreck last night.
1600 is the max, right?
Or
1000.
you're all of it. I've been tired today.
Let me guess, 2 hours of sleep though.
No, I think I cumulatively got 3 or 4. So I'm good.
Oh, it's a lot.
It's a lot. It is. It can be a lot some days. we're doing, we're going to take a light source, a monochromatic light source. Now I'm doing a light bulb, but of course, we're using a laser to do this better. So you get this monochromatic light source, light's going to come out in waves, and it's going to go through these slits, and it's going to, of course, come out of those, and it's going to hit this screen. Now, here's what we're looking for. We know that on this screen, we saw that we're going to get a spot, what we call a central maximum, a spot that's bright. Okay, so this is
that
right
right between the two slits too?
Yes. Our central maximum is exactly midpoint between these two slits. So I'm going to draw that better. Now, when we say slit separation here, like how far apart they are, we're talking like very, 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 very tiny, like hundreds, maybe even thousands of a millimeter. Okay, these are not very far apart. If they're too far apart, then things don't happen. We'll see that in a little bit. Okay, so we're going to have a central maximum that goes basically straight out, perpendicular to this this slit barrier. Okay. Now, what we also saw then, the central maximum is going to be really bright, by the way. We also saw that you would get a dark, but then another bright region, and then a dark, and then another bright region, and a dark, and then another bright region, et cetera, on either side of this. There we go.
Oh,
Okay.
that's
Now,
just like the sine of x, cosine of x.
it's a little bit like that, and there's a reason why. You will see a sine theta here somewhere. What we call these things, this is the central maximum. We say that that has an integer number of 0. Okay, you'll see these n's pop up in just a second as well. Where we have our very first maximum outside of our center, we call that n equals 1. This one's called n equals 2. This one's called n equals 3, etc., etc. On either side, you could label those out. So this is also n equals 1, n equals 2, n equals 3, etc. Okay, so these integers, these n numbers, are referring to which maximum away from the center are you? The first maximum away from the center, the second maximum, the third maximum. The center maximum, n equals 0. Okay? Now, our goal is to come up with a way to say, well, how far away are these maxima from that central maximum? Okay? So we say this is y sub n. Which n are you talking about? How far away is it? Okay, that's what we want to figure out. We want to have some expression that says y equals, and then a bunch of stuff that depends on things that we're dealing with. All right? So what could this possibly depend on? Well, let's take a look at a little picture that maybe illustrates pretty well what's going on. Not this one. This one. We saw this before. Okay? Look at what you've got going on here. All right? You've got, in this picture, these waves are coming out. Okay, this is a monochromatic light source, same wavelength. So all you have to do is say, well, let's count the wavelengths from the opening to the point of the screen that we're looking at. So we got 1 wavelength, 2, 3, 4, and 5 wavelengths for this bottom wave. This one up here, 1, 2, 3, 4.5 wavelengths. Okay, 5 wavelengths and 4.5 wavelengths. Notice when these two things get to that point, this trough, or this peak meets that trough, they cancel out. That's destructive interference. So if this is 5 wavelengths, this one's 4.5 wavelengths, that means that if these things are like a half a wavelength apart, you get destructive interference. Now you could have 1/2 wavelength apart. You could have 3/2 wavelengths apart, or 5/2, or 7/2, or 9/2. You can have any odd number of half wavelengths apart, you're going to get destructive interference. And that's what you would have as you go up farther and farther and farther. You'd have more half wavelengths apart. But in this case, over here, you've got 1, 2, 3, 4, 5.5 wavelengths from the opening to that spot. And this one you've got 1, 2, 3, 4.5 wavelengths. 5.5 and 4.5. But we still get constructive interference there. Notice that we have a peak and a peak that add together at that spot, effectively. So those things add together. Okay? These are going to differ by exactly, in this case, 1 wavelength. If they differed by exactly 2 wavelengths, would that matter? Would they still constructively interfere? Would they still add together if they're different by 2 wavelengths? Yep. You can differ by any number of integer wavelengths and still get constructive interference, because no matter what, you still have your peaks matching up with peaks, and your troughs matching up with troughs with constructive interference. Okay? So that's really what's going on here. If we change this angle, you can see if we change this angle, we change the distance from this slit to whatever spot we're looking at, and therefore we change the number of waves that fit there for each of these openings. And so we can change whether we get constructive or destructive interference depending if we look farther up the screen or farther down the screen. Okay, that's the basic idea here. So let's just work out some of the little tiny geometry that goes with it. It's not too bad. Okay, check this out. We're looking at, well, how do we know how far up the distance away from that central maximum that we're going to be for each of these constructive interferences? So we got to label some things. Here's what I'm going to label. The distance between the slit barrier and the screen, I'll just call that capital L. It's like a length, right? What I'm also going to say is that these waves come out of here and they hit some spot. We'll say that maximum right there. Any maximum, okay? Now these waves are, in general, both be coming out at about the same angle theta. Remember, these slits are so small, or so close together, that they have virtually the same angle that they go out. Okay? Now, here's the thing. This bottom wave has more wavelengths than this top wave. All right? How many more? Well, if I draw this little right triangle in here, the red, the blue, and the black, this little right triangle, if I look at this little section of that right triangle, this blue section down here, I call that some length S. If that length S is exactly equal to some number of integer wavelengths, if that is some integer number of wavelengths, then everything out here is going to be in phase, just like we saw in that last picture. This could be 2 wavelengths, it could be 3 wavelengths, it could be 1 wavelength, it could be no wavelengths. As long as it's 0, 1, 2, 3, etc., as long as we've got some integer number of wavelengths, then that half difference doesn't make a difference. We still get constructive interference. We get these things to be in phase. Okay? If that's going to be a half number of wavelengths, then you get destructive interference, then you're talking about this spot right there. Okay? So, what we want to do is we want to say, well, here's our slit separation distance. We'll call that D. Okay? Again, we're after how far away from the central maximum are these other maxima going to be. I'm going to do a little bit of kind of geometry in here. Check this out. We can say that S, this little length right here with this right triangle, is equal to D times the sine of this angle. D sine theta gives you your S. We also know from here that S, if we want constructive interference, has to be equal to some integer number of wavelengths for constructive interference. That's the condition that needs to be true. Okay, so what I'm going to do is I'm going to set these two sides of that equation equal to each other. Say D sine theta equals and lambda. And if you know something about L and Y, you can actually come up with a fairly interesting result. So this is actually kind of our general equation for, well, here's the condition that needs to be true. Here's the condition that needs to be true for constructive interference. Here's the cool thing. Watch this. Tangent, this angle. Looking at our geometry here, you can say the tangent of that angle is equal to y over L. We've got a bunch of right triangles in there. All right? Remember, these things are so close apart, or so close together that you can almost think of them as just being in the same spot in reality. So the tangent of that angle that we're looking up there from is going to be that y over the entire distance L. Now, here's the cool thing. This angle is so small that we use something we call a small angle approximation. You guys heard of this before? Small angle approximation. With very small angles, the tangent of that angle is basically equal to the sine of that angle. Okay? And so, with that approximation in mind, because we've got such long baselines between like the diffraction, or the two slits and the screen, and such small spaces between these two, between any two ends, we've got very small angles that we're actually talking about. We can say that this is a safe assumption to use at this point because we've got such small angles. Okay, so with that in mind, we can say that, well, if d sine theta equals n lambda, we can just change this into d instead of sine theta. We can use y over L equals n lambda. So I said, yes, we have a sine theta. Well, sine theta has a small angle to tangent theta. Tangent theta is equal to y over L. So I just plugged in y over L for my sine theta, and that thing way over there. And so now I'm going to rearrange this thing to give me my y. Okay, y equals n lambda times L over d. And this is what we call our two-slit interference. Two-slit, let's write it. Two-slit interference, small angle approximation. It works really well. It's an approximation, yes, it's not always exact, but holy cow, it works really well when you actually want to figure out how far away from the central maximum each one of these subsequent maxima are going to be. Okay? In this equation, n can be 0, 1, 2, 3, etc. It's an integer that starts with 0. If n is 0, you're looking at the central maximum. If n is 1, plug in n equals 1, then you're looking at this first maximum outside of the center. You're looking at how far away it is. N is 2, you're looking at how far away the second one is. N is 3, third one, etc. Okay? This is handy. Now, it seems kind of mundane why we're doing this. Once we get into a little bit of quantum physics, we're going to find out that any object you can think of, can potentially do this. A baseball, for example. A baseball can give you an interference pattern, or several baseballs. You just got to slow them down a whole bunch. Everything you can think of actually has a wavelength. Everything has a wavelength and has wave behavior. Okay?
Even human.
Even humans. All right, take one of these.
Stuff.
It's covered with letters and numbers.
Wasn't like that earlier.
Here's number 7. The idea behind number 7 is that they tell us that we've got some two-slit interference going on. They say that, hey, at the n equals 3 maximum, that sucker is exactly 6.6 centimeters away from the central maximum. Okay, so at n equals 3, the y value, the distance, is 6.6 centimeters. They say that the distance to the screen is 1.25 meters, and the slit distance, the slit separation distance, is 0.025 millimeters, which I just converted that into meters. All right, to have everything in consistent units. That's pretty typical, by the way, for slit separation. You're talking, a couple, maybe like 25 or so millionths of a meter. All right, it's pretty small. In fact, we're going to measure the width of a hair, which is going to be pretty similar to that same size. It's going to be tomorrow. Okay, so they're asking us, well, what's the wavelength of the light that gives you that interference pattern with those distances? Okay, so I can use my small angle approximation very easily on all these problems. So here's just that small angle approximation as I've written right there. Okay, I'm going to rearrange that for my lambda, because that's what I'm looking for, my wavelength. I know everything else. Okay, so lambda is y times d over nl. Right? My y is my 6.6 centimeters, which changed to meters. Here's my slit separation distance. In this case, they said it's the third maximum away from the center, so that means that n equals 3 for this particular part of the problem. And also I've got my L in there, 1.25. So that answer comes out to, let's plug and chug, 4.4 times 10 to the negative 7 meters.
Did that all letter B?
What's that?
Oh no, sorry.
Okay, yeah, 4.4 times negative 7 meters. I actually converted that right off the bat because I like to in nanometers. Because when I hear nanometers, I think of like wavelengths that I can actually see. 440 nanometers, you guys can actually see that. It's right around the violet, maybe blue-violet end of the spectrum. Okay, so that's part A. Part B then is saying, all right, use that result, use that wavelength that you found to now say how far away is my n equals 2 maximum going to be? What's the y value for that? How far away from the central maximum is it going to be?
I wouldn't say the exact.
Okay. So now we're looking for our y values that are instead of anything else. We got to plug in n equals 2. Our wavelength we found. The distance to the screen doesn't change. The distance separation of the slits doesn't change. And that one you should come up with about 4.4 centimeters. If you plug everything in.
How many nanometers on a meter?
That's most one that has.
A billion. Yeah, a nanometer is a billionth of a meter. A nanometer would be 10 to the negative 9.
I had blue in my
This is pretty similar to something we're going to do tomorrow. Okay, it's a very common thing in these things to have like a known wavelength of something, for example, and with that known wavelength to find the width of something like a hair, and then to use that hair width to find the wavelength of an unknown wavelength. Now it's kind of going back and forth. It's exactly what we're doing.
I'm scared.
Don't be scared. It's good.
I want to know this. I don't want to know the width of my hair.
Well, then don't use yours.
Use your dog.
You can. I mean, yesterday when I tried this out, I just found some hair on the ground and used that.
That's disgusting.
I wash my hands afterwards, I think.
No, it's
Everyone.
You think?
and then it's made of
What?
meal.
What?
Made meal afterwards.
I had a hair salad. There's nothing around here on the floor to fill your belly.
You don't have much time to cook anymore.
Yeah, do you remember there was one girl in Brooklyn, believe it or not, and she ate her hair. She
I
had
remember
like
drinking
a
that.
5-pound beer ball.
Yeah, that's
Yeah.
disgusting, but awesome. Okay,
Stop talking about it already.
so that's that. There are other problems on that sheet that in due time, sometime between now and next Wednesday, you should try out. I'll post the solutions to them sometime soon as well. Okay, so here's the thing. When we do our double slit interference, obviously the separation depends a lot on the separation of your maxima, depends a lot on the factors involved, like the wavelength of the light. It depends on the slit separation as well, that D. Okay, looking at our equation, looking at this one, if your slit separation becomes really, really, really big, big D, what happens to the separation between maxima?
Very, very, very small.
Very, very, very small. Okay? So as your D gets bigger and bigger and bigger and bigger, you get these maxima to shrink, 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 shrink. Come closer together, in other words. The extreme situation is where you have these slits that are really, really, really wide, really far apart. If you can get light through there, it's going to just look like a blur. Okay? You get such small separations. But really, really, really close slits, you get very wide separations between these two maxima. So this is just like a series of things getting farther and farther and farther and farther apart until you get like this blur of stuff. Okay, you know, like a spot. The equivalent of that is thinking about taking that laser light and just shining it through a window, just really wide. You get like no interference out of that. Okay. So that's a double slit interference. We've also got, wow, that's the wrong button. We've also got the single slit. If you run laser light through one single narrow slit, you get this very, very similar pattern. The difference between this pattern and the two slit is that in the single slit you get a much wider central maximum. That's going to be the biggest difference. All right. So let's see if we can actually see that with our laser. Yeah.
Ethan, put your hands together. You can't do it.
Yeah, it happens a lot.
Okay, watch your head. Watch your head. Okay, there's our awesome laser, I guess. Okay, laser light through double slit again. Looks like I'll do that. We get a very clear interference pattern. All right, on the screen.
Oh, there it is.
Below the words on the screen. Okay, interference pattern. Now, if I go through a single slit, I'll make it a better one. I don't know if you'll be able to see it or not. I don't know, you can see the central maximum. You're having an awful hard time seeing the other maximum. Let's see if we can get them here. Can we see any of the maxima? Yeah, let's try this one. There we go. Whoop. There it is. So this is just a single slit. That's it. A little bit wider one here. Okay, so we get the same kind of thing out of just one single slit, which is kind of unexpected because aren't we just shooting light through one single barrier or one single opening? And the answer is yeah, but not really. All right. Okay, so what we want to do is take a look real quick at why we get this to come out of, why we get this similar effect out of a single slit that we do out of a double. And we'll just derive our relationship for the distance between, in this case, minima, not maxima. And we're done. It'll go fast. Okay, same exact picture except a little bit different. There it is. Going to be number 7. Here is now our new situation. We have one single opening. This is just our single slit interference stuff. We're going to say that the width of that opening is just W. Okay. Now, we're going to take light, we're going to put it through that opening, and it's going to be incident on some barrier over here. And we saw that we get a central maximum, we get a minimum, and we get another maximum, a minimum, maximum, etc., etc. Alright. Now, analysis behind the single slit is a little bit more complex. Okay, so what we're going to do is just kind of simplify it as best we can. We're going to look at the light that comes past the very top of this barrier and just through the middle of that barrier. Okay, just through the middle of that barrier. Now, if we want this to hit one of these minima, okay, what we have to do is draw on a little triangle here. It's a smaller triangle because we're just using a smaller geometry. There we go. We're going to go through the same kind of analysis. We got this little path length S down here. S is going to be equal to, with our geometry over here, half W sine theta. Okay, half W sine theta. Here's half W. Here's sine theta, so your S is equal to half W sine theta. Now, the condition for destructive interference is when that path length is exactly equal to half an integer wavelength, right? Because the wavelengths have to be out of phase. The waves have to be out of phase at that spot. We're talking about half integers. Hey guys. Okay, so what I'm going to do then is I'm going to say this is for a minimum. For minimums, or for minima. Okay? Instead of having an n here to confuse ourselves, we're going to change that n into an m. Because with our two slit interference, we use n's. With our single slit interference, we're just going to use m's so that we know that we're talking about one or the other. One thing you just have to memorize. M's are for single slit, n's are for double slit. Okay, so that's going to be true. We've got half w sine theta from up here. And that's going to equal to half m lambda from right here. And that's going to give you a minimum. It's going to give you a destructive interference point. Our halves cancel out, and so we end up with w sine theta equals m lambda for a minimum. Okay, we're almost there. What I could do then is the exact same kind of analysis I did before. I say the separation between the opening and the screen is L. Okay. Now I'm going to be talking about what is the distance between the central maximum and that minimum. Y, so M I'll call it. All right. Same idea. Tangent of the angles is going to be Y over L, and of course we have a small angle approximation. So we could say that's basically equal to sine theta, small angle approximation. All right, almost there. So if sine theta is y over L, okay, plug it in right here. We have W times y over L equals m times lambda. And so we have almost the exact same formula, except now we've got y being a minimum equals m lambda L over our slit width. Okay, so m in this case equals 1, 2, 3, 4, 5, 6. So this is our small angle approximation. Small angle approximation for the distance to the minima, those dark spots. These dark spots that appear in our interference pattern. Okay, not the light spots, the dark spots. Okay, so this one right here, this dark spot, is called m equals 1. This one right here, m equals 2. This is an m equals 1. This is an m equals 2 right there. Okay, so we're saying, here's the central bright peak, the bright spot. Here's the first dark spot away from that. Here's the second dark spot away from that. Yeah?
What does the y?
Just means the distance to this particular dark spot. This is just a subscript. Yeah, the distance between the center of that central bright spot to that first dark spot. When m is equal to 1. It's 2, the second dark spot. Okay? It's a very, very, very similar equation to the two-slit interference, except that with single-slit interference we deal with minima. With two-slit interference we deal with maxima. That's the biggest difference. Same type of analysis. All right, now you know everything you need to know. Now it's just a matter of practice. So you've got these. Now you've got the information to solve all of them instead of just like half of them. Good shot. Work on a couple of these. Work on a few. After number 10, they go to single slit stuff, single slit diffraction or single slit interference.
What's the y and distance?
Oh, it's just a sub. It's just here's the distance. Y is the
I mean,
distance,
like,
right?
what is it on the graph?
Up here,
Yeah, like what is it?
it's the distance between the center of this whole thing and
Okay,
where that minimum appears. So if we're looking at those light and dark spots on our interference pattern. Find the center light spot, find the first dark spot away from that. What's the distance between the two? We're going to see all this tomorrow. Turns out that there's a guy named Babinet way back in the day, who's of course dead now. He said that, hey, instead of having like an opening here, you could actually just put a very, very thin barrier. And that thin barrier gives you the exact same result. In other words, we're going to take a hair off your head and have laser light shine across it. We're going to see the interference pattern because of it. It's awesome. Totally awesome. So, practice makes perfect. Practice, practice, practice. Maybe I'll do another example.
What was the location for the maxima for two-slit interference again?
The location of the maximum?
Yeah.
What do you mean?
Like the formula to find.